All right. Good morning, everyone. Happy Friday. Back to the class. All right. How's everyone? Good. Okay. So do not forget you have your tutorial 2 today for half of the class and the rest of you on Monday. The question for tutorial again is at the end of this notebook. And yes, today's tutorial number 2. All right, so let's continue with what we started on Wednesday. On Wednesday, we said we are on categories of single degree of freedom yet, still, right? One variable, but this time we add a force, an external force, which is harmonic to the system. This force can be something sine or something cosine omega t, and this omega is the frequency that we apply that load. So it's not just a constant load, it's a harmonic force. And what we refer to this ft, we call it the forcing, to this omega, we call it the forcing frequency. All right? So this omega. We draw our free body diagrams, and then we find the equation of motion, which turned out to be this equation. Somebody asked last Wednesday, somebody asked, so we use the Newton law. Can we use the Lagrange equation when we have an external load? The answer is yes. And in fact, your tutorial, your TA today will show you how you can deal with the Lagrange equation when you have a force. But just to give you a heads up, if you recall the Lagrange equation, I'm just going to write it at the corner, has this form, d over dt. Let me write it down small. What's that one? This one, dt. So if you recall, the Lagrange equation was like this form, d dt, derivative of t with respect to x dot, or variable, plus derivative of u with respect to x. This is equal to 0, right? That was the Lagrange equation. We find t, we find u, and we take the derivative with respect to x dot and x. If we have an external load, this thing is not going to be 0. It will be the force in the direction of the x, whatever force we have, which in this scenario, the force is simply ft or f0 cosine omega t. In Lagrange equation, it will be shown by q. So this q is the external load in the direction of that derivative that we use. If it's a rotational, so this can be a force or a moment. A force, or it can be a moment, because instead of a force that I apply to this system linearly, it can be a couple or a moment that I apply and back and forth, a harmonic moment. All right. So again, your TA will show you today or on Monday, depends on the session you go, how you can use Lagrange equation for when you have a forcing frequency. But let's continue with the solution that we got last day. We said that this equation, it's a second order and it's non-zero. So we have f0 cosine omega t. To solve it, our solution has a complementary solution, xp, and a particular solution, xc and xp, complementary and particular solution, right? The complementary solution is for when we set it to 0. Just again, a refresher for you, if you had your differential equation math course long time ago. And we guess an answer. This answer we previously found for this equation, which was in the form of a cosine omega nt and sine omega nt, which omega n is square root of k over n. We don't have any control on this part of the equation because omega n depends on k and m. The only things that we can control is a and b, which a and b depends on initial condition. And then we said the equation has also a particular solution. The particular solution, we showed it by xp, and this xp, again, we rely on guess. Sometimes, or most of the times in differential equation, we look at the form of the differential equation and we guess something. xp is x cosine omega t. All right, so that's our xp, which is x cosine omega t. So what we do, we take the derivative of this xp, we put it in the equation, which we did last day, and we find this x. So this x, we claim it's a constant. We don't know what it is, but we found it. We put all of them together. This is our final answer. So xt is a cosine omega t, b sine omega t, and this is the particular solution, right? This was the xc part, and this is the xp part. Now, if we have the initial condition, so initial condition when t is 0, I put t equal to 0. Let's see, xt is a number, x0, and I solve this equation. I do the same for the x dot. I ended up finding a and b, which is this long form for xt. This is what we found last time, right? We said the equation of motion for this system is this long form. And something that I wanted your attention was that you can look at this answer as two waves adding together. One is a wave which has a frequency of omega n, right? That frequency of omega n, it depends on the natural frequency of the system, or it depends on the characteristic of the system, like stiffness and mass. And then it has a forcing frequency, which is up to us, depends on how fast, if it is a motor is rotating, if it is a, let's say, washing machine, which we will solve one example soon, how fast is rotating. So this omega is the forcing frequency, right? From this diagram, this is this external load. But in general, we say the answer to this system is two waves superimposed, or two waves adding to each other. Then we said, let's plot these things for an example, which you have the code on Canvas if you want to try it. So the same equation, I put it like on MATLAB here. Nothing special, we put the values, and I just change these values omega. Okay, so let's start with omega 5. If I plot these things, all right, so I will get this answer. So I put some values for k and m here, which you can see it on this document. We selected k to be 100,000, m is 10 kilograms. So immediately I realized my natural frequency, k over m, gives me 100 hertz, right? And then I have x0, v0, I put all of them here. It's just a simple function. We plot this simple function, and for omega equals to 5, we get this answer. This is nothing but two waves superimposed on top of each other. One of them has this a small frequency, right? Like this big wave, small frequency wave, and another one is a high frequency wave going ups and down. Right? So the small frequency, sorry, the high frequency is being moved by the lower frequency. Let's change this omega according to what we suggested here. We suggested here start with omega 5 hertz, then try 10 hertz. Let's try 10 hertz. So if I put 10 there, and you have this code, you can try it on your own later. Again, nothing special about it. So, different graphs. Again, you can see the frequency now is 10. If you count the number of peak here, Oh, I forgot the mouse. So if you count the number of peak here, you will see there are 10 because the frequency was 10 and the omega n, those high natural frequency, they are staying the same because omega n is the same, right? But if you count, there are 10 peaks here. So let's change the frequency to the next one. The next one, it says 30. Okay. So let's change it to 30. All right. Let's run it. So a different wave. The shape is changing because I'm changing the forcing frequency. So two waves add together, and it has some like a random shape. You can still see those peaks ups and down, but it's not really as easy to distinguish like when we had a very low frequency. For example, when I had 5. Then next suggestion is to try frequency of 90 hertz. Let's try 90 hertz. So if I go with 90, all right. So now we can see a pattern here, right? With the frequency of 90 hertz, it looks like that the amplitude is increasing, then gets to 0, then increase, then gets to 0, right? So we can think of it as more like a beating. It goes up, down, right? This is a phenomenon, in fact, that happens and people refers to it as beating phenomenon. Okay, so beating always happens when there are two waves. Okay, two waves that natural frequencies, they are close to each other. Remember the scenario that we tried was 90 hertz and our natural frequency is 100 hertz. When the forcing frequency and natural frequencies are close to each other, we will get this phenomenon, which is called beating. Again, to remind you, remember we are plotting this function. We have omega and we have omega n. Omega n, we don't have any control. That's the natural frequency. It's 100 hertz. I change omega from 5, then 10, 30. When I hit 90, then I can see this phenomenon, which is interesting, right? It's, again, the amplitude of vibration goes up and then come down. And it's not just for mechanical vibration. Let's say if I play two sound with exact same frequency, okay, from like two microphones, you can try it if you have two cell phones at home. If you try, let's say playing a sound with exact same frequency, so nothing will happen. But if you play one with, let's say, 100 hertz and another one with 90 hertz, these two sound waves combine with each other, and then you're going to hear a sound that goes up, 0, goes up, 0. I have, like, it's funny that on YouTube you can find everything. Like people post everything. And I just Googled before class, and somebody tried that with two cell phones. Like he played a sound. Let's see what will happen. I guess I need to put my microphone probably there. So see, the frequencies are 800. So just pay attention to these like frequency that is playing. One is 800 hertz and another one is 801. So there is, like, if you pay attention, there is this beating going up, down, up, down. And it's, I know it's a little bit annoying, but just for the sake of seeing what happens. can move it back. You can check it later, but going back to that beating happens when we excite the system with a frequency that is close to its natural frequency. Now let's try 99.9 hertz, almost 200 hertz, and see what will happen. So this time, so what was the value? It was 99.9. So if I play, okay. So this time we will see the amplitude is keep increasing, right? And it starts from 0 and gets up to very large amplitude. And if you continue, it is for 5 seconds, it's going to go to infinity eventually. So, and this is a phenomenon which we call it resonance. And resonance happens if the natural frequency and the forcing frequency, they are almost equal to each other. Why I didn't put 100? Let's try 100, exactly the same frequency. So you will see that MATLAB probably gives us nothing, right? Because if I go back to the equation and over here, if I put omega over here equal, not that one. So if I put omega exactly equal to omega n and simplify the equation, I will show you in a moment that this equation is not going to be valid. Right? Let's summarize then based on what we plot. We have a simple system. We plugged in some numbers and we realized that depends on forcing frequency, we are going to see different response. Two phenomena that may happen is one is beating. Beating happens if the forcing and natural frequencies are close to each other. And then the second one is resonance, when the natural frequency and forcing frequency are exactly matched with each other. Let's figure out the math and see how it goes. All right. All right. So first let's start with the beating. The beating, as you saw in those graphs, it was something going ups, down, and ups and down. Let's show it in the math formula and see what is the function xt over here. For simplicity, let's see that, let's set the initial condition to be 0. So for simplicity, let's set x0 to be 0 and v0 to be 0, right? Then what do I get? I will get, so let me copy the whole equation. That's a long equation. So I'm just gonna replace x0 equal to 0 in this equation and v0 equal to 0, right? And let's move back here. So I would get xt equal to, let me move back, what do I get? This one is 0, so it will be minus f0 k. Okay. So f0 k minus m omega square cosine omega t minus cosine omega n t. Okay, so I haven't done anything special. I just, in this equation, long equation, I substitute x0 equal to 0 and v0 equal to 0, just for the simplicity, for the sake of the rest of discussion that we are going to have. So I hope I didn't do the math wrong. Yep, that's correct. So this is negative, this is positive. So this is my response. All right. Now I'm going to manipulate this equation a little bit. And let's define, omega n plus omega divided by 2, let's call it omega bar, or omega average. Let's show it by omega bar. And let's define omega n minus omega divided by 2. Let's call this one delta omega. This is what we define. We define omega bar as the average and delta omega, the difference divided by 2. Using these two equations, I can find omega, which is, if I add them together, I can find omega and omega n. So omega will be then omega bar plus delta omega, and omega n will be omega bar minus delta omega. Please check my math to make sure this is correct. So if I add these two equations, I would get omega n, which is omega bar plus, no, this is omega n. So this is omega. And if I subtract them, omega bar minus omega, yes, I would get that. Okay. Now let's get back to xt. I'm just going to focus on this part. I'm just going to simplify this omega t minus cosine omega nt, and then see what do I get. So I will get cosine omega bar minus delta omega minus cosine omega bar plus delta omega. In a moment, you will see where I'm getting them. But we're just going to manipulate these equations, simplify it, so then we can get more meaning out of it. Okay, you see what happened so far? We define omega bar and delta omega. We have two equations. We solve these two equations, and we get omega n and omega. And please check my math to make sure these plus and minus are correct. Then I substitute these omega n and omega in this xt. And this, whatever I have inside that bracket, I'm going to work around that bracket things and see what do I get out of it. Now, a little bit of trigonometry. Who remembers the cosine alpha plus beta from high school or maybe earlier courses? It was something like cosine alpha, cosine beta. Is it minus or positive or plus? Sine alpha, sine beta. Am I correct? You can check it online to make sure that I'm correct. Hopefully I'm correct. But now that we know how to expand these things, we should be able to expand this cosine, these things, and minus cosine that thing. And then we do lots of math. And I'm just going to write down the final answer, which is sine 2 sine omega bar t sine delta omega t. Yes.
On that line, are you using the cosine omega bar minus delta omega?
There will be a, sorry, a t. A t. Oh, you're right. Somewhere there is t. You're right. We forget these t things. Thank you. So please correct this typo. So we have this t as well. Right? We just substitute omega and omega n, and we have this t. So if we do all this math, spend 15 minutes on it. We will not 15 minutes, maybe 5-10 minutes, and then we will get to these final answers. So my xt, then I simplify it to be f0 or 2f0 k minus m omega squared sine delta omega t sine omega bar t. I just write it in this form. Okay. Now, why I write it like that one? So we can think of these function now as two waves multiplying by each other. All right. The first wave, like inside this bracket, is it is delta omega is a low frequency thing, right? This is delta omega, and what was delta omega? Was the difference between these two divided by 2, which, if you recall, we said we want these two numbers to be close to each other, right? Two close number, you subtract, divided by 2, you get a very small number. So this, you have this delta omega. So then if delta omega is a small number, you have all these. Oh, sorry, it is a small, so it is like a wave like that. Okay, so that's inside the bracket. That's one wave. This value is a constant. And this omega bar t, omega bar now is a big number compared with delta omega. It is the average of these two, right? This is omega bar. And it gives me like a high frequency wave. And what we did, we multiplied these two waves together. Right? So what I'm getting out of it, this is what we say, that we have a wave, high frequency wave, and this high frequency wave, its amplitude, we say it's being modulated by a low frequency wave. Right? And you can see this high frequency wave here. This is the high frequency wave, but its amplitude is being trimmed or being controlled by this low wave. And the terminology that we use, we say a wave, its amplitude is being modulated, is being controlled by another wave. And this is where the beating happens because of this controlling the amplitude. We start from 0, the amplitude increase to maximum, then again 0, and then keep increasing and 0. Similar to that sound, if you could hear it, it goes up, down, up, down. Yes.
I'm just wondering, is the omega n like for the definition of delta omega, shouldn't it just be the natural frequency minus the
this is the way that we define it, because we wanted our equation to look nice, but you can define it. So that's a good question. He's asking, should we, when we define delta omega, should we include or not include this divide by 2? This is the way we define it. And just because at the end, I didn't want to have a leftover 2 in my equation. Yeah, that's our definition. But intuitively, when we talk about delta of something, we like to subtract them. But again, I didn't want a leftover 2 somewhere in the equation. That's why I defined it like that. Okay, so again, going back to this wave, I hope you understand what happened. We have 2 waves, right? These 2 waves, if their natural frequencies are close to each other, like this example, omega is 0.9% of or 90% of omega n, we are going to have 2 waves superimposed on each other. And one is a high frequency going ups, down, but its amplitude is not constant. If we only had this one, this amplitude is constant, right? But the inside bracket, it's controlling this wave, and its amplitude is going up, down, and that's why we could hear that beating sound, right? So a little bit of information on this graph. This high frequency that we plot here, right? The distance between these. That's the high frequency one. It is 2 pi over omega bar, right? That's the time between the peaks of this high frequency, 2 pi over omega bar. And the distance between, let's say, one complete cycle for the yellow one, for the one that I highlighted, is 2 pi over delta omega, right? So if this is 2 pi over delta omega, then I can say then a distance between like over here and here is half of that, right? So this distance then I claim is pi over delta omega. If I substitute delta omega by that things that we had, so it will be equal to 2 pi over omega n minus omega. And this is what people call the beating frequency. So it is called beating frequency. Like because it's a beating between 0 and another 0. 0 goes up, gets to 0. So that time it's called the beating frequency. And if you notice outside, or sometimes in the machine, it happens. And you're going to see more examples of this beating. So we show it, I write it down then over here, T beat, or sorry, beating, not frequency, beating period, or beating time. T beat is going to be 2 pi over omega n minus omega. So this is a time that it takes between each beat, right? A little bit of math, but just focus on the concept. The math, you can work around it. It's not really that complicated. We work with the original equation. We set x0 and b0 to 0. I just manipulate the data, not the data, the equation. And I got to this form because I wanted to have two sinusoidal or cosine multiplying by each other. So I concluded that the result of when I have beating is two functions being multiplied by each other. This a slow frequency one, right, and this high frequency one. We multiply them and we get to this beating phenomenon. Any question for this one? Hopefully it's clear. But please go and play with this code and put different values. As I said in this example, you saw it clearly for a very simple case. When we have the natural frequency 100 hertz, we change omega from 5, nothing happened, right? Let's go, if I have the frequency again, set equal to 5. So only things that I can see here is a big wave, right, which has 5 peaks. If you count them, 1, 2, 3, 4, 5, because we had 5 hertz the frequency. And those high frequency, which was, if you count them, it's going to be 100. Or because it's, sorry, 5 seconds, it's going to be, right, so you can count them and see how many they are. So that's the natural frequency. Now, if I change these things instead of 5 to 90 or 95, then this is what will happen, the beating, okay, for a very simple case. Now let's figure out the math for the other one, for the resonance. So our conclusion for resonance was that our original answer, let's write it down, mx double dot plus kx equal to f0 cosine omega t. So we find the solution xt to be a cosine omega nt plus b sine omega nt, and then f0 k minus m omega squared cosine omega t. This was the answer. However, when we have omega equal to omega n, we will see there is a problem. Let's write down this part of equation. It will be f0 k minus m omega n squared, right? For omega n squared, I have a formula. It is k over m, and this is infinity. So it is wrong. Therefore, our solution is wrong. Remember, we had to start with a guess, right? We had to guess something and we got to this. However, we were not lucky, and for one case, the answer is wrong. It's not mathematically correct. So we need to try something else. So let's then try again. Let's this time the particular solution, because you see the problem is with the particular solution, right? This was a particular solution, or XP. And there was something wrong with this one. You see, mathematically it's not correct. So this time, XT, let's try X like a constant, then multiply by T, sine omega T. But omega is equal to omega n. I just put omega n there. Remember, we are solving this equation for not a general case. We are solving it for omega equal to omega n. And this is what we guess. We guess that might be the answer. We don't know for sure, but we guess that might be the answer. Again, if you recall in differential equation, sometimes we have to rely on guess and try and see if it works or not. Let's try that one. I take the derivative and I put it in the equation to see what will happen. So this is my equation then, mx double dot plus kx equal to f0 cosine omega nt. Remember, I replace omega with omega n, and I claim that xp is the answer. So I need x double dot p and xp. All right, I need to take the derivative of that things. X dot p is equal to, and you need to check my derivative, make sure that I'm correct. So x sine omega nt, right? And then if I take the derivative one more time, it's going to be x omega n t cosine omega nt. Please check to make sure it's correct. So I'm taking the derivative. I have t here, I have t there. First, I take the derivative with respect to t. So I get x sine omega t. But that's correct, hopefully. Now we need x double dot p. Okay, that one is long. Let's be careful not to make mistake. X omega n cosine omega nt, right? And then the second one will be minus x omega n squared t sine omega nt. And then I have plus x omega n cosine omega nt. I hope I didn't make a mistake. But please check to make sure. Okay. So we got x dot and x double dot. I can simplify x double dot a little bit more. So it will be 2x omega n cosine omega nt minus x omega n squared t sine omega n t. Don't be scared of this equation. We don't really need them that much. It's just for proving the concept. And just you get, a little bit where these things come from. So let's put them back into that equation and see what will happen. M, so what I need to do then, I put everything and substituting everything's here. So I will have mx double dot p, which we concluded it is 2x omega n cosine omega n t minus x omega n squared t sine omega n t, right? This is x double dot p plus k xp. xp is k x, where is xp? Okay, that's our xp. K xt sine omega n t, all of it equal to f0 cosine omega n t. Remember, we substitute everything there. All right, what should we do with this equation? Now I get confused. Oh, we can do one thing with it. This omega n, we know what's its value, right? We know omega n is k over n. So this guy, because it has a square, is k over n. So there is a hope to simplify things. This n will be canceled by this n, and the whole things here will be canceled by these things. I was hoping that it might be simpler than that. So in that case, what do I end up with? So these two then cancel each other, right? If we put equal to k over n. So I will end up with 2m omega n cosine omega n t over here has to be equal to f0 cosine omega n t, and it gives me, and I have one big x here, of course. It gives me x is equal to f0 2m omega n. Okay, that ugly equation I didn't expect to get to this simple form. f0 2m omega n. Okay, what we are looking after then? We are looking to find the final answer, right? The final answer now, xp is, okay, we find x, or let's say put the whole things. So xt is a cosine omega nt b sine omega nt plus xp that we just find xp f0 2m omega n sine omega n t. Okay, so this is then the final answer when omega is equal to omega, and we have a t here. There is a t over here, right? Remember, this is our xp. This is xp, and this guy here is xc. Where we said our answer is xp plus xc. So for general case, the answer is xt, that big equation up there, which a and b we can find them from the initial condition. For a special case when omega is omega n, omega is equal to omega n, xt is this form, right? Omega is equal to omega n. Now I have just one wave, not two, and they are omega n. You see, they are all omega n. Previous answer, it had omega and it had omega n. So where this increasing then come from? See here, like the amplitude is keep increasing with time. Where it comes from? The problem is this t over there, right? There is a t over there in the equation that keep increasing the amplitude. I hope I didn't confuse you. Later, when you check on the math, you'll see it's not really that complicated. It's very simple. But anyway, so let's summarize. Two phenomena. One is beating, and another one was resonance. Resonance, we figured that our initial guess, our initial answer that we are happy with it is not correct. So we had to guess another answer. We guess another answer for xp because xp was the trouble, right? Because we showed here at omega equal omega n, we get to infinity. Mathematically, it's not correct. We try this x t sine omega n t. We substitute it, simplify it, and this is what we ended up. One wave with the frequency of omega n, right? But it has this guy over here, this t. And this t making the trouble because as the time increase, the amplitude keep increasing. Okay? And this is end up with resonance. And resonance happens in machines a lot. And that is the cause of many bridges fail. On YouTube, just check bridges fail due to resonance. You will see very fun videos. I guarantee. So just check bridges, famous bridges collapse because of resonance. Okay, have a good day. And do not forget about your tutorial. As I said at the beginning, your tutorial, can I have your attention for another 30 seconds, please? Your tutorial today and on Monday will show you the Lagrange equation when you have external load. And do not forget quiz 1. See you on Monday. Please review this material. On Monday, we go with the steady state response.